All right, we're going to try to do this. I was reading through Theorem 38 that y'all were asked to prove, and we got at different levels of correctness on this, and I just wanted to go through this completely with y'all and see if we could come up with something a little bit better. All right, so we're going to see what we can do here. So to start with, we're going to do the A implies B part, okay? And I'm actually going to split this into two cases. So case 1 and case 2. Now, if you remember, the theorem itself actually talked about the idea that parallel lines implied that the lines were both vertical or they had the same slope. So case 1 is that they have the same slope. So the given here that we're going to start with is that L is parallel to K, right? Now, if we're going to do that, we need to have L and K. So I'm going to cover here, and I'm going to draw two lines. That's a messy one. That is equally messy, but we'll take it. Okay? And then we'd have Y right there, X right there. So I'm going to label this as the X-axis. This is the Y-axis. This is L, and this is K, all right? So we're starting with the assumption that these two lines are parallel. And what I did here was I constructed Y and X-axis, which means that, and I'm going to go ahead and say that these are perpendicular, that Y is perpendicular to X, okay? So we know this is perpendicular right here. Now, I'm not going to leave that there because I'm actually going to reuse this diagram for another part of the proof. So that's just really what I'm going to construct. So, and then I'm going to come through and I'm going to make some label. Label, okay, I'm just going to do some labelings here. So angle 1, angle 2, angle 3, angle 4, angle 5, angle 6, and these are more global labelings for the entire proof. So angle 1, 2, 3, that is not quite visible, 3, 4, 5, and 6. All right. And I'm also going to label A, B, C, D, and E. Okay, make that A a little bit better. All right, so there are those. And then I labeled my points there. So my 5 points, or intersection points, however you want to label those. A, B, E, C, and D. So those 5 points. So labeled those angles and labeled points. A, B, C, D, and E. Now, is this section entirely necessary? You can make an argument that we don't necessarily have to talk about these labelings, we can just do them. But if we want to be really precise about what we're doing here, then yeah, we want to go ahead and label them because we need to know where these pieces come from. Because the idea is the proof needs to stand alone. We don't need any additional explanation. Someone should be able to come and look at this and see exactly what we did and where everything came from. So from there, we're going to come along and we're going to say, well, now that we have this labeling here, what else can we do? What else do we know? Well, one of the things we know is that since L is parallel to K, we also now know that 1 is congruent to 6. And we know that 2 is congruent to 5. All right? And that is based upon alternate interior angles of parallel lines. Okay? And then we also know that angle 3 and angle 4, I forgot my angle sign there, are right angles because X and Y are perpendicular, right? Now, look at what we now have there. We have these three angles of ABE congruent to these three angles of CDE. Okay? So by angle, 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 triangle ABE is similar to triangle CDE. Right? And that was the big piece. This section up here was the big piece that most of you missed when we were posting this theorem, as you just directly went to the idea that these two triangles were similar. And now the triangles are similar, well then we actually know a bunch of other stuff. And by definition of similar triangles, okay, by definition of similar polygons actually, not just triangles, but polygons in general, we know that AB to E, AE is equal to DC to DE. But that one's not really useful to us because what we really want is we want to set up this idea of slope, which would be the change in X over the change in Y, which would be these two sides right here from EB and EA. So the ratio we want to use is BE is over, let's see here, EA is equal to CE over DE. And this is just one of those situations where the direction of the letters doesn't matter quite as much. If you really want to be nitpicky about it, BE is going down, so that would actually be a negative value. So if you wanted to be really precise about it, instead of using BE, we would use EB. All right, listen. There we go, B. EA, well, that's actually, again, backwards, so if we want to be really precise, we'd be going forwards with it, all right? So that would be AE. And then we want to do the same thing with the others. CE is actually backwards. DE is actually the right direction, so that's actually the only one that's in the right direction with that, okay? And I'll talk about why this direction matters here in just a second, okay? So we have that. Also, by another theorem, we know by, I think it's E36 in the theorems we've been working on, and this is actually another theorem that someone else will be proving, we know that by definition slope is y2 minus y1 over x2 minus x1, which is essentially saying the change in y over the change in x. Now going back to the idea of why we had to have these in orders, and I actually did this on purpose to kind of make a point to bring your attention to that I purposely and intentionally changed the order. EB goes from where to where? It starts here and it goes up there. So what are we doing? We're doing the change from one point to the other in the vertical direction or on the y-axis, right? The change in the y value. So the y value changed. We're doing the change in the x value. So what we're doing, what I'm purposely doing here with these values here is I'm orienting them so they're all going in the same direction. We're going from A to E. We're going from E to C, right? That way we're keeping, oh, there's a mistake, all right? DE and EC are upside down, right? Okay, so we're going from D to E, and then we're going from E to C. So I actually had that backwards. So E to B is up, D to E is up. A to E is left to right, E to C is left to right. So when we look at the triangle, we want those to be matched up. And now we have those matched up. So the idea here is that this is what this slope means. Now that we have this slope set up that way, right, we know that these two pieces right here are the slopes. So this would be slope 1, and this would be slope 2, right? And we don't necessarily need this piece as a part of the proof, but what we do need is this definition tells us that this is what slope is defined as being. These are defined as being the slopes. So if you want to, we could say that or we can now make this statement that the slope of L is equal to the slope of K, right? And that's what we were wanting to show. So that's the first, so that is proving case one of from A to B. Now case two is actually still starting with the idea that the lines are parallel. So case two is still, you got this given that L is parallel to K. And in class, this is the part that I said is a little trivial, right? And the reason I said it was trivial is because it's actually a very straightforward and very quick part of this. So if we know that L is parallel to K, that's the piece we start off knowing. And we say, and the theorem was saying that they're both that if they are parallel, then they both have to be vertical or they both have to have the same slope. So one thing we can say here is that L is parallel to K. That's a given. And then we can say, well, what if L is vertical? Okay, so we're making this assumption. And then the idea here is that we could actually do case 2A and case 2B, where we start with L as vertical and then we do K as vertical. But really what you're going to see here is it doesn't really matter which one we start with because it's arbitrary to begin with. So what I'm starting with is that L is vertical. Well, if L is vertical, what else do we know? We know that the y-axis, by definition, is vertical. And if we know that the y-axis is vertical and and L is vertical, then we now know that L is parallel to the y-axis, again by that definition. So if y is parallel to L, that means that, I'll probably strike that. If L is parallel to y, that means by a previous theorem that K is also parallel to y, right? Which means that L and K are both vertical. All right? So they're both vertical lines. So we started with the assumption that one was vertical, and that means the other one has to be vertical if they're both parallel. And a pushback that I can understand on this one is that, well, you're starting with the assumption that one of them is vertical. Yes, you are. We're starting with the assumption that they are either, that one's not vertical, and one, meaning one has a slope, and then we showed in the previous part, in case one, that if L had a slope of m1, then K had a slope of m2, we should then show that m1 and m2 are equal to each other. They have the same slope. So here we're saying, well, L is vertical, which means it has no slope, and that's another piece you could put right here if you wanted. It has no slope, right? Again, because if it doesn't have m1 as its slope, it means it has no slope. So that's the other case, okay, that we're making here, is it has a slope of something arbitrary, or it has no slope, which means it's vertical. And we happen to know that the y-axis is also vertical, which means it has no slope, which is why it fits here so nicely, which means that y is parallel to L. And if these two are parallel, and we already know that K is parallel to L, then we know that K is now parallel to Y, which means that K is also vertical because it means it also has no slope by definition of what it means for the lines to be vertical. And that fulfills case 2 for us, okay? Now, what we need to do is we need to do the B implies A, and it has case 1, and we're going to do a case 2 with it. And this one goes a little bit faster than case 1 for the other one. But here what we're doing, the thing we're going to assume is that, using that same diagram that we had before, that L has a slope of m1, and I'm going to let that be equal to BE over EA. And if we need to, we can go back and make sure that we get this set up correctly. Okay, so what we want to do is we make sure we're going in the same direction. We're going up and we're going right. So let's make sure that we're going up. BE, well, that's actually going down. So that's actually backwards. EA, EA is actually going backwards as well. So that's actually a negative over a negative. They're both going the wrong direction, so that actually is okay. So we could leave it like that if we wanted to, if that makes sense. If it causes you issue, you can pause the video and make your own adjustments as you need to. Has a slope of, let's see here, M2, and in this case we're saying that it is, let's make sure we get this one out, EC, which is your run, and DE, which is your up piece. So you're going right and up. So DE over EC, okay? So DE over EC, okay? And in case 1 here, the thing that we're saying, the place we're starting with is that the slope 1 is equal to slope 2. Okay, so all this right here, all we did here was just simply make a label. This isn't even part of the definition right there or a given. This is the given, okay? That M1 equals M2. And you don't have to label these as M1 and M2. You could have done BE over EA equals DE over EC. You could have set those equal to each other. I did this because I thought it might help with the flow a little bit better for the second part. Now, since we are still dealing with this being superimposed on the XY axis, we still know that the Y axis is perpendicular to the X axis, right? We still know that. So y-axis is equal to the x-axis. That's a big piece that we know. And if that is true, think about what else we know. Well, we come back up here. We know that angle 3 and angle 4, again, are both right angles. So that implies that angle 3 and angle 4 are right angles. So I don't know what I put an F on the end of so for. So angle 3 is congruent to angle 4. Now that's important because we now have two angles of two different triangles that are equal to each other, or congruent to each other. And by M1 being equal to M2, we also now have the ratio of one triangle equal to the ratio of another triangle. So by definition, what we now have is that by side angle side similarity, triangle ABE is similar to triangle CDE, right? And if that's true, that means that angle, let's go back up here just for a second. We have these two triangles are equal to each other, right? That means that angle 2 is congruent to angle 5 and 6 is congruent to 1 because they're similar triangles. So by definition, angle 1 is congruent to, which one was that? 6, okay? Angle 6. And that's actually all we need, okay? And this is by definition of similar polygons. Sorry about the handwriting, guys. Okay? Similar polygons. So if angle 1 is equal to angle 6, that means that L is parallel to K by alternate interior angles are congruent, right, of parallel lines. Okay, now. That's it. We showed the parallel lines. So we started with the slopes being equal, and we showed that the lines have to be parallel. But we have case 2, okay? So now that we have case 1 done, let's look at case 2. Case 2 here is actually fairly straightforward. Here we're starting with the idea that L and K are vertical. On the last one, and again, this is the pushback I know I'm probably going to get, is that, well, last time we said they were parallel and then we assumed one to be vertical. Yes, we did. Here we're saying they're both vertical, okay? We're not saying either of them are parallel to anything. We're saying they're both vertical. That's the assumption here. So the given here is they are both vertical. Okay. Now what does that mean? Well, or what else do we know? Well, we know the y-axis is a vertical axis by definition of the way the y-axis is constructed in the coordinate plane. All right. So if that's true, then L is parallel to y and K is parallel to y because they're parallel to vertical lines, which means that L, that's a horrible L, L is parallel to K. Okay? And that's by one of our previous theorems that we proved. And now we've proven everything we need here. Okay? So I know there are probably a lot of questions about this. I'm going to try to clean up the video a little bit for you. But please ask questions as needed. I'm going to post this video in the comments, and please make comments about this video in comparison to what you did on what you turned in. Okay? Thank you.